Pick up a rock, any rock you like, hold it in your hand. Feel the weight of it. Squeeze it. Really try to push your thumb into it. You can't, obviously you can't, it's a rock. Rocks are solid. Rocks are solid. But let me ask you something. Why? I don't mean what is it made of? You know what it's made of. Atoms. Everybody knows that. I mean, why is it solid? Why can't your thumb go through it? Because here's what we know about that rock. Every atom in it is almost entirely empty space. If you took a single atom and blew it up to the size of a football stadium, the nucleus, the part with almost all the mass, would be a marble sitting on the 50-yard line. And the electrons, tiny specks, impossibly small, buzzing around somewhere up in the last row of seats. And in between, nothing. Vacuum, emptiness. So the rock in your hand is, by volume, 99.999999999999999. 9% empty. I'm not exaggerating, I'm rounding down. And your thumb, same thing, empty. So what you've got when you press your thumb against the rock is two enormous clouds of nothingness refusing to pass through each other. Like two fogs that somehow can't merge, two ghosts that somehow can't walk through the same wall. You do this every day without thinking. You pick things up, you put them down, you sit on chairs, and stand on floors, and lean against walls. And every single one of those interactions, every time one object stops another object from passing through it, is a miracle. I don't use that word lightly. It is a miracle in the precise sense that classical physics cannot fully explain it. That is deeply strange, and the answer to why it happens is, I believe, the most terrifying single fact in all of physics. It comes down to one property of one particle, one tiny, abstract, invisible feature of the electron. Change that feature by even the smallest amount, and your rock disintegrates, your hand disintegrates, the chair you're sitting on, the floor beneath it, the building around you, the earth itself, every star in the sky, all of it collapses into a formless, featureless mush. Everything you have ever touched, everything you have ever seen, every object that has ever existed is standing on the edge of a cliff, and the only thing keeping it from falling off is one rule that one particle follows. So let's find out what the rule is. And let's start with something so simple you'll think I'm wasting your time. Take the simplest atom in the universe. Hydrogen. One proton sitting in the middle, one electron somewhere around it. I say somewhere because the electron is not orbiting like a tiny planet. I know you've seen that picture in textbooks, little circles with dots running around them like a miniature solar system. Forget that picture. It's wrong. The electron is more like a fog. A cloud of probability. Doesn't have a position until you look. You can only say there's a certain chance of finding it here and a certain chance of finding it there. The cloud is thickest close to the nucleus and fades as you move outward. In hydrogen, that cloud settles into the lowest energy state it can find, the most compact, most stable configuration. We call it the ground state, the 1s orbital. The electron parks there as close to the nucleus as quantum mechanics allows, and life is simple. Quiet, unremarkable. Now let's build helium. Add a second proton to the nucleus, toss in two neutrons for stability, and add a second electron. Both electrons settle into that same ground state orbital. Both of them fit. The cloud gets a bit tighter because the nucleus is now more strongly charged, pulling harder, but the basic picture is the same. Two electrons, one orbital ground state. They're like two people sharing a park bench, slightly crowded maybe, but it works. So far, nothing interesting has happened. You're probably wondering when I'll get to the point. Be patient. Now add one more proton, one more electron. Lithium, element number 3. And something happens that should make you sit up straight. That third electron does not join the other two. It can't. It's not allowed. Something in the deepest structure of reality reaches in and says, no, you may not sit here, go find another seat. And the third electron is exiled to a higher energy state. The next shell out, farther from the nucleus, held more loosely, easier to strip away, like being told the ground floor apartment is full and you have to live on the second floor where the walls are thinner and the wind blows harder. That matters enormously. Because helium with two electrons in the ground state is one of the most chemically inert substances in the universe. It doesn't react with anything, it just sits there serene and untouchable. But lithium with that one extra electron pushed up to a higher level is a wildly reactive metal. Drop it in water and it fizzes. It catches fire, it wants to give that outer electron away to anybody who'll take it. The difference between an inert noble gas and an alkali metal that explodes in water is exactly one electron being told, you can't sit there. Why can't it sit there? Let me show you. Every electron in an atom is described by a set of 4 numbers. Think of it as a quantum address, a unique identifier. The first number, n, tells you the energy level, roughly how far from the nucleus you are. The second number, L, tells you the shape of the orbital. Some are spherical, like a ball. Others are shaped like dumbbells or clover leaves or stranger things. The third number, mem sub L, tells you the orientation of that orbital in space, which direction it points. 3 numbers, 3 parts of the address. But there's a fourth number, and the fourth number is the strange one. It's called spin, and it has only 2 possible values, up or down, plus 1/2 or minus 1/2. That's all. 2 choices. And from those 2 choices, everything follows. Now, spin is one of the most misleading names in physics. The electron is not spinning. Not like a basketball on a fingertip, not like the Earth on its axis. If it were physically spinning, the surface of the electron would have to move faster than light, which is forbidden. Spin is not a rotation, it is an intrinsic quantum property. It has no classical equivalent. You can't picture it accurately, so don't try too hard. Just know this, every electron carries this property. It always has the value 1/2, and it can point in one of 2 directions, up or down, that's it. In 1922, Otto Stern and Walter Gerlach did a beautiful experiment. They shot a beam of silver atoms through an inhomogeneous magnetic field, a field that was stronger on one side than the other. Classical physics predicted the beam should spread out smoothly, like a flashlight beam hitting fog, smearing into a broad patch on the detector screen. Instead, the beam split into 2 clean spots, 2 and only 2. Not a smear, not 3 spots, not 5, 2. The whole laboratory went quiet when they saw the result. Because classical physics says angular momentum can point in any direction, a spinning top can tilt at any angle, there should be a continuous range of deflections. But nature said no, exactly 2. Take it or leave it. That was the first hard experimental evidence that something about the internal structure of atoms comes in exactly 2 flavors. A few years later, George Uhlenbeck and Samuel Goudsmit, 2 graduate students in Leiden, the Netherlands, proposed the interpretation. The electron itself carries a kind of angular momentum, an intrinsic twist, that can point in only 2 directions relative to any axis you choose. They called it spin. Their advisor, Paul Ehrenfest, was initially skeptical. He told them it was either very important or nonsense. He encouraged them to publish. They did, and it turned out to be very important indeed. Dirac, in 1928, derived the relativistic equation for the electron and showed that spin emerges naturally. You don't have to add it by hand. It falls out of the marriage between quantum mechanics and Einstein's special relativity. The Dirac equation predicts that the electron has spin 1/2, with 2 possible orientations. It also predicted the existence of antimatter, the positron, which was discovered 4 years later. Not a bad week's work for one equation. But the reason spin matters for our story isn't the magnetism, and it isn't the antimatter. It's what happens when you combine spin with a principle that Wolfgang Pauli announced in 1925. Pauli was a remarkable person, brilliant, sharp-tongued, famously rude. He once dismissed a paper by saying it wasn't even wrong. But he was the kind of physicist who could intimidate anyone in a room just by sitting in the front row and shaking his head. But he was also extraordinarily perceptive. In the early 1920s, everyone was staring at the periodic table and going crazy. The pattern was beautiful. 2 elements in the first row, 8 in the second, 8 in the third, then 18, then 18, then 32. Why those numbers? Bohr had a model of the atom with electrons in orbits, but the model couldn't explain why the orbits filled up. Why didn't all the electrons just fall into the lowest orbit? Edmund Stoner, an English physicist, published a paper in 1924 showing that the number of electrons in each completed shell was exactly equal to the number of distinct quantum states available at that energy level if you counted a mysterious extra 2-fold splitting. Pauli read Stoner's paper and saw the pattern. He said later it was Stoner who gave him the final clue. And the clue was this: the complicated structure of the periodic table becomes perfectly simple if you adopt one rule. No 2 electrons in an atom can have the same values of all 4 quantum numbers. Every electron must have a unique quantum address. Address: if one electron is in the state n equals 1, L equals 0, M sub L equals 0, spin up, then no other electron in that atom can occupy that exact same state. That seat is taken, the Pauli exclusion principle. 5 words that explain everything. Now you might think I'm being dramatic. 5 words that explain everything. Really, let me prove it to you. Let me walk you through it carefully, because I want you to feel how much falls out of this. Go back to helium. 2 electrons, both in the n equals 1 shell, both in the n equals 0 orbital, both with M sub L equals 0. The only thing that can differ between them is spin. One is plus 1/2, one is minus 1/2. Both spin slots filled. The ground state is now at capacity. 2 electrons per orbit, no more. So when lithium's third electron shows up, every available quantum state in the lowest shell is occupied. Every combination of quantum numbers at n equals 1 is taken. The third electron must move to n equals 2, a higher energy, a larger orbital, farther from the nucleus. And that electron pushed out to the second shell is the one that makes lithium a metal. It's the one that makes lithium reactive. It's loosely held, easy to share or surrender. That single expelled electron is the entire basis of lithium's chemistry. Continue. Beryllium has 4 electrons. The fourth fills the second slot in the n equals 2, L equals 0 orbital. Boron has 5. And now the L equals 1 orbitals start filling, the p orbitals shaped like dumbbells pointing along different axes. Carbon has 6, nitrogen 7, oxygen 8, fluorine 9, neon 10, and the second shell is full. All the quantum addresses in n equals 2 are occupied. Neon is an inert gas, just like helium. It doesn't react. It has no reason to. Its house is full. Then sodium comes along with 11 electrons, and that 11th electron, just like lithium's third, gets pushed to the next shell. N equals 3. And sodium, just like lithium, is a reactive alkali metal that explodes in water. Every step, every element is the exclusion principle, forcing electrons into the next available slot. The entire periodic table, all 100+ elements, every chemical property, every reactivity pattern, every bond type, all of it is a consequence of electrons following Pauli's rule. Before Pauli, the periodic table was a mystery, wrapped in a pattern. Mendeleev had arranged the elements by weight and noticed that properties repeated with a rhythm. 2, then 8, then 8, then 18. Chemists used this pattern brilliantly, predicting undiscovered elements and their properties, but nobody could explain why the rhythm existed. Why 2? Why 8? Why not 5 or 12? Pauli's exclusion principle answered every one of those questions in a single stroke. 2, because there are 2 spin states in the n equals 1 shell. 8, because there are 8 distinct quantum states in the n equals 2 shell, 4 orbitals times 2 spins. 18, because n equals 3 adds d orbitals and more combinations. The numbers aren't mysterious, they're counting quantum addresses. And the exclusion principle says each address gets 1 tenant. Carbon has 4 electrons in its outer shell, arranged in a specific pattern of orbitals. Those 4 electrons can form 4 bonds, pointing roughly toward the corners of a tetrahedron. That tetrahedral geometry is not a choice. It's a consequence of which orbitals are filled and which are available, which is determined entirely by the exclusion principle. And that geometry, that precise spatial arrangement, is the backbone of every organic molecule. Every protein, every strand of DNA, every sugar molecule, your cells burn for energy. Oxygen has 6 outer electrons. 2 of them are paired. 2 orbitals are available for bonding. The bonds form at an angle of about 104.5 degrees. That angle is why water is bent. And because water is bent, it's a polar molecule with a slight positive end and a slight negative end. And because it's polar, it dissolves salts, sugars, and amino acids. It's the solvent that makes biochemistry possible. The angle of a water molecule, the shape of a carbon bond, the reactivity of iron, the conductivity of copper, the inertness of gold. All of these are downstream of the exclusion principle. All of them. You are a chemical machine, an extraordinarily complicated one, but a chemical machine nonetheless. And every chemical reaction that keeps you alive, every enzyme that folds into its precise shape, every neurotransmitter that crosses a synapse, every hemoglobin molecule that grabs an oxygen atom in your lungs and carries it to your muscles, depends on molecules whose shapes are governed by electron orbitals, whose filling patterns are dictated by a rule stated by a 25-year-old Austrian in 1925. Iron has a particular electron configuration that lets the hemoglobin in your blood bond loosely to oxygen. Loosely is critical. If the bond were too strong, oxygen would stick and never let go. If it were too weak, it would fall off before reaching your cells. The bond strength is exactly right because the d orbitals of iron, shaped and filled according to the exclusion principle, create precisely the right geometry and energy level for a reversible attachment. You breathe because of the exclusion principle. Every single breath. And it goes beyond individual molecules. The reason you can smell a rose is that specific molecules fit into specific receptors in your nose, like keys and locks. Those shapes, both the key and the lock, are determined by chemical bonds, which are determined by electron orbitals, which are determined by the exclusion principle. You smell a rose because electrons obey Pauli's rule. The sentence sounds absurd, but it's not. It's exactly what's happening. But I haven't told you the really alarming part yet. But forget chemistry for a minute. Forget molecules and reactions. Let's go more fundamental. Why is the floor solid? Why doesn't your chair sink into the ground? Why does matter take up space? You might guess it's electrical repulsion. Atoms have negatively charged electron clouds on the outside, and two negative charges repel each other. When your shoe pushes on the floor, the electrons in your shoe repel the electrons in the floor, and that's what holds you up. And that's partly right. Electromagnetic forces are involved, but they're not the whole story. They're not even the main story. In 1967, Feynman, Dyson, and Andrew Lenard published a landmark paper. They sat down with the mathematics and asked, take a bunch of electrons and nuclei interacting through electromagnetic forces. Will they form stable extended objects, or will they collapse? The answer depends entirely on whether the electrons are fermions. If the electrons obey the exclusion principle, the energy of the system grows proportionally to the number of particles. Double the matter, double the energy. Everything is well behaved. Atoms have definite sizes. Solids resist compression. Tables exist. Floors work. You can stand on things. But if the electrons do not obey the exclusion principle, if they behave like bosons and happily crowd into the same state, the mathematics gives you a catastrophe. The energy doesn't grow linearly. It grows as the number of particles raised to a higher power, somewhere around the 7/5 power. The system is thermodynamically unstable. All the atoms rush inward, collapsing. The energy released is colossal. Dyson himself was rather eloquent about this. He said that without the exclusion principle, not only would matter not be stable, it would collapse, and the released energy would be comparable to a nuclear explosion per atom, not per kilogram, per atom. Now, the Dyson-Lenard proof was, by their own admission, extraordinarily complicated. Dyson-Lenard said their proof was so unilluminating that it inspired Elliott Lieb and Walter Thuring to find a better one in 1975. And Lieb and Thuring did find a better proof, more physical, more transparent. But the conclusion was the same. The stability of matter requires the exclusion principle. Full stop. So the ground beneath you right now is not just electromagnetically supported. It is quantum mechanically constructed. The exclusion principle inflates atoms to their actual sizes, prevents them from collapsing, gives matter its rigidity, and makes the floor something you can stand on. Paul Ehrenfest, a beautiful physicist, one of the deepest thinkers I ever knew, once asked, "Why are atoms so big?" And he answered his own question. Only the Pauli principle. He saw it clearly in the 1930s. Without the exclusion principle, electrons would crowd into the lowest state, and atoms would shrink to a tiny fraction of their actual size. The principle is what inflates them, gives them volume, gives you volume. You occupy space because electrons refuse to share quantum addresses. Let me give you a way to feel this in your bones. Imagine you have a box and you start putting electrons in it. The first electron finds the lowest energy state, settles right in. The second electron shares that state, but takes the opposite spin. Fine. The third electron is forced to the next energy level. The fourth joins it with opposite spin. You keep adding electrons. Each new electron has to find a higher and higher energy state because everything below is occupied. These higher energy electrons are moving faster. They're more agitated. They push outward harder. And the more electrons you pack in, the harder the remaining electrons push back because you're forcing them into increasingly cramped quantum real estate. This is nothing like filling a jar with sand. Sand doesn't resist harder the more you add. Electrons do. Each additional electron raises the stakes. The resistance grows. It gets harder and harder to compress. That's what's happening when you push on a rock. The electrons in the rock are in a quantum mechanical traffic jam. You're trying to squeeze them into states that are already taken, and they won't budge. Not because they're tough, not because they're heavy, because the mathematics of their wave function literally does not permit two of them in the same state. Your body occupies a certain volume of space right now. That volume is a direct consequence of the exclusion principle. You are as big as you are because your electrons are spread across enough energy levels to give your atoms their sizes. Think about what that means. If I could somehow turn off the exclusion principle for just the atoms in your body, every electron would plummet to the ground state. Your atoms would shrink to something fantastically small. You would collapse, not into a smaller person, into a point, practically. A microscopic speck of ultra-dense matter, surrounded by an eruption of energy that would make a hydrogen bomb look gentle. You are, right now at this very moment, a thermonuclear weapon held in shape by a quantum mechanical grammatical rule. Have I frightened you yet? Good, let me make it worse. Let's leave the Earth. Let's fly out past the solar system and find a white dwarf star. A white dwarf is what remains after a star like our sun has burned through all its fuel. The nuclear furnace shuts down. The outward pressure from fusion, the thing that held the star up against gravity, disappears, and the star begins to collapse inward under its own weight. In a normal gas, pressure comes from heat. Particles bounce around, banging into each other, pushing outward. But as the star collapses and the matter gets squeezed tighter and tighter, something new happens. The electrons get packed so close together that they start running out of quantum states. The lowest states fill up, then the next ones, then the next, and the exclusion principle says, stop, no more. You can't put any more electrons into those states. They're full. They're full. So the electrons are forced into higher and higher energy levels. They move faster and faster, not because they're hot, but because there are no low energy states left, and this forced acceleration creates an outward pressure, degeneracy pressure, a pressure that has absolutely nothing to do with temperature. It exists purely because electrons refuse to be in the same quantum state. That's worth pausing over. In everyday life, pressure comes from heat. You heat a gas. The particles move faster. The pressure goes up. Cool it down. The pressure drops. But degeneracy pressure doesn't care about temperature. You could cool a white dwarf to absolute zero, and the pressure would remain, because the pressure comes from the exclusion principle, not from thermal motion. The electrons aren't pushing outward because they're energetic. They're pushing outward because there's nowhere else to go. That pressure is what holds up a white dwarf, an object roughly the mass of our sun compressed into a ball the size of the Earth. A teaspoon of white dwarf material weighs about 15 tons, and the whole thing is supported not by heat, not by nuclear reactions, but by the stubbornness of electrons following Pauli's rule. In the 1930s, Subramanian Chandrasekhar, a young Indian physicist barely 20 years old, performed one of the most remarkable calculations in the history of astrophysics. He was on a ship sailing from Madras to Cambridge to begin his graduate studies. He had weeks with nothing to do but think, and he started working out the structure of white dwarfs using the new quantum mechanics and the exclusion principle. What he found shocked the scientific establishment. He showed there was a maximum mass a white dwarf can have. Beyond that limit, even degeneracy pressure can't hold back gravity. The star must collapse further. Chandrasekhar calculated the limit to be about 1.44 times the mass of our sun. We call it the Chandrasekhar limit, and it's one of the most important numbers in astrophysics. Arthur Eddington, one of the most famous astrophysicists alive at the time, publicly ridiculed Chandrasekhar's result. He essentially said it was absurd, that nature would never allow such a thing to happen. He was wrong. Nature doesn't care what humans find absurd. The Chandrasekhar limit is real, and it determines the fate of every dying star in the universe. Beyond that limit, gravity wins. The electrons are crushed into the protons, forming neutrons. And now it's neutron degeneracy pressure, the same exclusion principle but applied to neutrons instead of electrons, that holds the star up. You get a neutron star. something the mass of the sun packed into a sphere about 12 miles across. A sugar cube's worth of neutron star material weighs about 1 billion tons. And the whole thing is held up by the exclusion principle. And if the neutron star is too massive, then even neutron degeneracy pressure isn't enough. Gravity overwhelms everything. And you get a black hole, a region of space where matter has collapsed beyond the point of no return, where no known force, not even the exclusion principle, can prevent total gravitational collapse. So the exclusion principle doesn't just hold up your coffee table. It draws the line between white dwarfs and neutron stars. It draws the line between neutron stars and black holes. The entire taxonomy of how stars die, the entire structure of stellar corpses, is governed by the same rule that decides whether lithium is a metal or a noble gas. One rule, from the table in your kitchen to the graveyard of stars, and I have to point out something subtle here, something that trips up even professional physicists if they're not careful. The exclusion principle is not a force. Repeat that to yourself. It is not a force. When I say degeneracy pressure holds up a white dwarf, your brain naturally pictures something pushing, like steam in a boiler or compressed air in a tire, something exerting a push, but that's not what's happening. There is no exclusion force, there is no particle exchange that mediates it. It doesn't travel at any speed, it's not transmitted through space. What's happening is more subtle, and I think more beautiful. The exclusion principle constrains the set of possible quantum states. It limits what configurations are allowed. And when you limit the allowed configurations, the average energy of the system changes. That change in energy as a function of volume looks like a pressure from the outside. But from the inside, nobody is pushing. The electrons are simply filling the only states available to them. And those states happen to have high energy because all the low energy states are taken. It's the difference between a crowd being pushed out of a building by fire hoses and a crowd spreading through a building because every room they enter is already occupied, so they have to keep climbing to higher floors. Nobody is pushing them. They're just looking for an empty room. That's degeneracy pressure. And that distinction between a force and a constraint matters deeply because it means the exclusion principle operates at a more fundamental level than any force. Forces are carried by particles. The electromagnetic force is carried by photons. The strong force by gluons. Gravity presumably by gravitons, though we haven't found those yet. But the exclusion principle isn't carried by anything. It's a property of the wave function itself, a rule about the allowed states of reality. Now let me show you why all of this is terrifying at the deepest level. Why do electrons obey the exclusion principle? The mathematical answer comes from something called the spin statistics theorem. Pauli himself proved the definitive version of it in 1940. The theorem says particles with half-integer spin, 1/2, 3/2, 5/2, and so on, must have antisymmetric wave functions. And particles with integer spin, 0, 1, 2, must have symmetric wave functions. Antisymmetric, let me explain what that means, because it's the key. Imagine you have two electrons. Electron A is in state 1, and electron B is in state 2. The wave function of the whole system depends on both electrons. Now swap them, put A in state 2 and B in state 1. If the wave function is antisymmetric, then swapping the two particles multiplies the wave function by -1. It flips sign. So the wave function with A in state 1 and B in state 2 is the negative of the wave function with B in state 1 and A in state 2. Now, what if both electrons are in the same state? State 1 equals state 2. Swap them. Nothing has physically changed. The wave function must be the same. But the antisymmetry rule says it must also pick up a minus sign. The wave function must equal its own negative. The only number that satisfies that condition is 0. The wave function is identically 0. The probability is 0. The configuration does not exist. That's the exclusion principle. Not a separate postulate glued onto quantum mechanics, but an inevitable consequence of antisymmetric wave functions. And the antisymmetry, according to the spin statistics theorem, is required by the marriage of quantum mechanics and special relativity. Let me give you an analogy, because I think this point is worth lingering on. Imagine you have a piece of paper, and you're writing a function on it, a function that takes two inputs, say the positions of two particles. And the rule is, whenever you swap the two inputs, the output must flip sign. If the function gave you +5 before, it has to give you -5 after the swap. Now try to write a function like that where both inputs are the same. If position 1 equals position 2, then swapping them changes nothing. The inputs are identical before and after the swap, so the output has to be the same. But the rule also says the output must flip sign, the same and also the negative of itself. The only possibility is 0. This isn't a prohibition enforced by some cosmic police officer. It's a mathematical impossibility. It's like asking what number is both 3 and -3. There is no such number. The question has no answer. And in quantum mechanics, when the wave function is 0, the probability is 0. Not small, not unlikely, 0. It cannot happen. So the exclusion principle isn't nature saying you're not allowed. It's nature saying that configuration doesn't exist in the space of possible realities. There's no state to forbid, because there's no state. So the chain goes, relativity demands that the speed of light is the maximum speed for anything. Quantum field theory, built on that relativistic foundation, demands that half-integer spin particles have antisymmetric wave functions. Antisymmetry demands the exclusion principle. The exclusion principle demands atomic shells, the periodic table, chemistry, molecular biology, solid matter, stellar structure. At the bottom, the speed of light. At the top, But there's a gap in this beautiful chain. The spin statistics theorem tells you that if electrons have spin 1/2, they must be fermions, and they must obey the exclusion principle. It tells you why the connection between spin and statistics must hold, but it does not tell you why electrons have spin 1/2 in the first place. It takes that as input, not output. Why does the electron have spin 1/2 and not spin 0? Spin 0 would make it a boson. Bosons don't obey the exclusion principle. They love being in the same state. They pile in, all of them like photons in a laser beam, trillions of them in the same quantum state marching together. If electrons had spin 0, every electron in every atom would drop to the ground state. No shells, no levels, no outer electrons, no chemical bonds, no molecules, no water, no DNA, no proteins, no cells, no life, no you, no me. Let me paint that picture more vividly, because I want you to really see it. In this hypothetical boson-electron universe, every atom would be a tiny, dense ball. Hydrogen would have 1 electron in the ground state. Fine, same as now. Helium would have 2, same as now. But lithium, 3 electrons, all crammed into the ground state. No electron pushed upstairs. No outer electron. No reactivity. Lithium would be inert, just like helium. Carbon, all 6 electrons packed into the ground state. No tetrahedral bonding geometry. No organic chemistry. Iron, all 26 electrons in the ground state. No d-orbital chemistry, no magnetism, no hemoglobin. Every element in the periodic table would behave the same way. Tiny, dense, chemically dead. There would be no periodic table at all, really, because the whole point of the periodic table is that properties repeat as shells fill and empty. No shells, no repetition, no table. The universe would have atoms, sure, and those atoms might clump together under gravity. You could perhaps have planets made of this featureless matter, but they'd be extraordinarily dense, small, boring spheres. No surface features, no minerals, no crystals, no oceans, because water can't form, no atmosphere, because gas molecules can't form, just dense pellets of matter sitting in the dark. No stars either, at least not the kind we know. The nuclear reactions inside stars depend on the structure of atomic nuclei and the quantum tunneling of protons, which involves details of nuclear physics that might still work. But even if you had nuclear fusion producing energy, there'd be no complex atoms to do anything interesting with that energy. Starlight would fall on planets where nothing could absorb it selectively, because selective absorption requires electron transitions between distinct energy levels, and there are no distinct levels when everything's in the ground state. A universe of light falling on dead rocks, forever. Nothing but dense, inert, featureless atomic pellets sitting in a structureless void. A universe of sameness, infinite and dead. That is what we are one quantum number away from. The difference between this universe with its stars and planets and oceans and forests and music and mathematics and love and a universe of nothing is the spin of the electron. 1/2 versus 0. That's the margin, and nobody can tell you why the number is 1/2. The standard model of particle physics describes what exists. It tells you the electron has spin 1/2 and charge -1 and a particular mass, but it doesn't tell you why those numbers and not others. They are parameters, settings, inputs. The machine runs beautifully with those settings, but the machine didn't choose them. As far as we know, they simply are what they are. You exist because of a setting nobody chose and nobody can explain. Some people, when they hear this, want to invoke a designer, some higher intelligence, that carefully set the dial to 1/2. And I understand the impulse. When you see a machine this intricate, this beautiful, working this perfectly, it's natural to ask who built it. But that question is beyond what physics can answer. Physics tells you what the settings are and what happens because of them. It doesn't tell you who picked them or whether anyone did. That's a question for philosophers and theologians, and I leave them to it. What I can tell you as a physicist is this. The margin is terrifyingly thin. Spin 1/2 gives you everything. Spin 0 gives you nothing. There's no graceful degradation, no halfway case where you get some chemistry and not others. It's all or nothing. Binary. The universe has structure, or it doesn't. And it just happens that we live in the version that does. Let me try one more angle, because I want to make sure you see just how pervasive this rule is. Think about metals. Why is copper a good conductor of electricity? Why does current flow through a wire? You might say the electrons move, and you'd be right. In a metal, the outer electrons of the atoms are shared across the entire lattice. They form a kind of sea of electrons, a Fermi sea, flowing freely through the material, but the exclusion principle determines the structure of that sea. The electrons fill up quantum states from the lowest energy upward, 2 per state, 1 spin up and 1 spin down, until all the electrons are accommodated. The boundary, the highest filled state, is called the Fermi energy, and only the electrons near that boundary, near the surface of the Fermi sea, can actually participate in conduction. The ones deep below are locked in. They can't accelerate in response to an electric field because the states they'd need to move into are already occupied. Only the electrons at the top of the pile have room to maneuver. That's why metals conduct, and it's why insulators don't. In an insulator, the band of filled states is separated from the next available band by an energy gap. There's no room near the Fermi energy for electrons to move. The exclusion principle, by filling states from the bottom up, creates the distinction between a conductor and an insulator, between a copper wire and a piece of glass, between a thing that carries electricity and a thing that blocks it. And here's a twist that's just delicious. At very, very low temperatures, something bizarre happens in certain metals. Electrons, which are fermions, that obey the exclusion principle, pair up. 2 electrons form a bound pair, called a Cooper pair, named after Leon Cooper, who figured this out in 1956. And here's the punchline. A pair of fermions, 2 spin 1/2 particles bound together, behaves like a boson. The pair has integer spin, and bosons don't obey the exclusion principle. So these Cooper pairs can all drop into the same quantum state. Every single one of them. They condense into a single collective quantum state that flows without resistance. No friction, no heat, no energy loss. The electrical resistance drops to exactly 0. That's superconductivity. And it's the exclusion principle coming full circle. The principle creates the normal behavior of metals by filling energy bands. And then under extreme conditions, electrons find a loophole. They pair up, become bosons, escape the exclusion principle, and flow without resistance. The rule creates the structure, and then the particles find a way around the rule, and that creates something extraordinary too. Nature is endlessly inventive. And notice what happened there. The exclusion principle creates structure by forbidding sameness, but nature finds ways to get around the forbidding, by combining forbidden particles into allowed combinations. 2 fermions, each individually prohibited from sharing a state, bind together and become a boson that faces no such prohibition. The restriction creates the structure, and the workaround creates something the structure alone could never produce. It's like a city with strict zoning laws that accidentally creates the conditions for a black market. The rules generate the loophole that generates something new. Transistors, semiconductors. It's every computer chip, every phone, every digital device you have ever used works because the exclusion principle creates energy bands and gaps in the electron structure of solids. Silicon, doped with tiny amounts of other elements, has its band structure modified just enough to switch between conducting and insulating depending on an applied voltage. That switching is the basis of digital logic. Every 0 and 1, every computation, every image on your screen, every word and every message you've ever sent was processed by a machine whose fundamental operation depends on the exclusion principle, structuring how electrons fill energy states in a crystal of silicon. So add that to the list. Chemistry, biology, stellar structure, the solidity of matter, electrical conduction, semiconductors, computers, all of it, every single one, a downstream consequence of the fact that electrons have spin 1/2 and obey the exclusion principle. I sometimes wonder if there is any fact about nature that has more consequences per syllable. No two electrons in the same quantum state, 12 words, and from those 12 words you get the periodic table, organic chemistry, molecular biology, the stability of matter, the structure of stars, the existence of metals, and the entire digital age. 12 words, an entire universe. Let me leave you with one last thought, and it's the thought that I find most unsettling of all. We said the exclusion principle prevents two electrons from being in the same quantum state. But how does an electron know? If there's one electron already in the ground state of a helium atom, spin up, and a second electron approaches, how does the second one know that spin up is taken? Is there a tiny sign on the door? Does the first electron send a signal? No. The answer is more subtle and more disturbing than that. The exclusion principle is not a force. It's not a repulsion. It's not a communication. It's a structural property of the wave function itself. The wave function of the entire system, all the electrons together, is antisymmetric. It's built that way from the start. The mathematics doesn't allow a configuration where two electrons share all 4 quantum numbers. It's not that the configuration is forbidden. It's that the configuration doesn't exist. The wave function for that configuration is 0. There is no such state. It's as if the universe has a grammar, and certain sentences perfectly well formed in English are not grammatically valid in the language of nature. 2 electrons in the same quantum state is not a sentence nature can utter. Not because something stops it, because the language has no words for it. The vocabulary of reality simply doesn't include that combination. And this is perhaps the deepest lesson of quantum mechanics. The universe is not built from things. It's built from rules about how things can be arranged. The rules come first, the things come second. Matter doesn't obey the exclusion principle, the way a driver obeys a speed limit, reluctantly and only when a cop is watching. The exclusion principle is woven into the fabric of what matter is. It's not a constraint on matter, it's a definition of matter. Take that away and you don't just get different matter. You get no matter. Not in any sense that would be recognizable. You get a universe where nothing is distinguishable from anything else, where everything is the same temperature, the same density, the same nothingness. I've spent my whole career marveling at how nature works. And the thing that amazes me most is not any particular discovery or any particular equation. It's the layering. The way one simple rule, stated in a single sentence, cascades upward through level after level of complexity until it produces everything. Atoms, molecules, cells, organisms, brains, civilizations. That grammatical rule, that structural constraint on what can be said in the language of quantum mechanics is what produces everything. The architecture of atoms, the shape of molecules, the hardness of rock, the brightness of stars, the rhythm of the periodic table, the conductivity of metals, the click of a transistor, the rhythm of the periodic table, the beat of your heart, the thought you're having right now as you listen to me say this. So the next time you pick up a rock and feel it resist, remember you're not touching atoms. You're not even touching electrons, you're touching a mathematical constraint, a symmetry property of the wave function, an abstract rule about how nature uses numbers. And that rule, that one rule, is the only thing standing between this world and oblivion. People sometimes ask me, Feynman, doesn't understanding the mechanism take away the beauty? When you know why the sky is the blue less beautiful? And my answer has always been no. Understanding adds, it doesn't subtract. But this, the exclusion principle, this goes beyond adding beauty. This adds terror. Because once you see how much depends on how little, once you see that the entire elaborate, gorgeous, intricate structure of reality rests on a single quantum number that nobody can explain, you realize something that changes how you look at the world. Every sunrise, Every heartbeat, every thought forming in your brain right now. All of it contingent on the spin of the electron being exactly what it is. Not slightly different, not approximately right, exactly one half. No tolerance, no margin for error, and nature hit the mark. Or rather, nature is the mark. One spin, one rule, one universe. And if that doesn't make you pause just for a moment and marvel at how strange and precarious and beautiful this whole arrangement is, then I haven't done my job today. Here's what I'd like to know from you. Before all this, what did you think was responsible for making matter solid? What was your picture? I'm genuinely curious what people carry around in their heads about this. Tell me your version and I'll tell you how close you were.